Welcome to this explainer. Look, if you're studying chemistry or the life sciences, you know exactly why we're here today. Exam season is creeping up fast, and you need to lock in those maximum marks on the heavy-hitter topics. So, we're conquering the galvanic cell. Specifically, we're going to break down exactly how to construct the absolute perfect, top-tier university exam answer all about the salt bridge.
Picture this. You're sitting in the exam hall, right? The clock's ticking down, the paper flips over, and boom, there it is, the dreaded galvanic cell question. It's a classic for sure, but man, it's also where a lot of students just bleed easy points by being way too vague or totally missing the underlying mechanisms. Well, today we're giving you the foolproof, step-by-step blueprint to totally ace it. We're taking those standard beginner explanations and leveling them up into precise, rigorous, exam-ready preparation.
Okay, so here's our exam blueprint for today. We're looking at the anatomy of the bridge. Step 1, completing the circuit. Step 2, electrical neutrality. Step 3, preventing liquid mixing. And finally, I've got a secret exam tip for you on ionic mobility. Let's get right into it.
First up, the anatomy of the bridge, or as I like to call it, the jello-like hero. Now, when you're actually asked to define a salt bridge, you absolutely need precision. You've got to say it's a U-shaped tube filled with an inert electrolyte suspended in a gelatinous medium that connects two half cells. Definitely make sure to write down that exact technical phrasing. Honestly, using these specific words shows your professor you understand exactly what the salt bridge physically is. It just sets a remarkably strong foundation for the rest of your answer.
To really lock in those initial points, you got to break down the essential components. First, there's your U-shaped glass tube. Then, the inert electrolytes. Now, pro tip, make sure you actually name drop specific inert electrolytes here. Please don't just write chemicals, be specific. Go with potassium chloride, potassium nitrate, or ammonium nitrate. Oh, and you definitely don't want to forget to mention its quirky gelatinous medium, specifically agar-agar. Throwing around correct technical terminology like agar-agar and inert electrolyte is literally a massive green flag to whoever is grading your paper.
Moving on to step 1, completing the circuit and bridging that electrochemical gap.
Notice how elegantly this whole system is just split right down the middle. On the exam, you need to deeply contrast the external flow with the internal flow. So point out that the external flow consists of electrons traveling freely through an outside metallic wire straight from the anode to the cathode. But here's the kicker. A circuit, by its very definition, has to be a complete unbroken loop. And that is exactly where the internal flow comes in. The salt bridge allows the physical movement of ions between the oxidation and reduction compartments. By contrasting these two totally separate flows, you brilliantly illustrate how the bridge completes the entire electrical system.
All right, here we go. Step 2, electrical neutrality. This is the absolute core mechanism.
Listen up, because this is where you're going to earn the absolute bulk of your marks. You really want to vividly describe the impending crisis of the galvanic cell. See, during continuous operation, at the anode, oxidation is constantly happening. And this creates a really dangerous, rapid accumulation of excess positive cations. Think zinc 2+ ions aggressively piling up in the solution. Meanwhile, over at the cathode, reduction is actively consuming metal cations. And what does that leave behind? A massive excess of negative anions like sulfate. Without immediate intervention, this rapidly growing charge buildup spells absolute disaster for the battery.
And you absolutely need to know the technical name for that disaster. Drop this exact magic term right into your exam paper: liquid junction potential. If that aggressive charge accumulation just continues completely unchecked, it generates a liquid junction potential. So what is that? Well, it's a newly created voltage across the boundary of the electrolyte solutions that actively opposes your electron flow. It's basically the ultimate villain of electrochemistry. It'll quickly kill the battery and cause the whole cell to just stop working entirely. No one wants that.
So, the crucial point you have to make is how this system actually saves itself. Enter the salt bridge rescue mission. Think of the salt bridge as this microscopic, high-speed traffic controller. To stop the liquid junction potential dead in its tracks, it deploys its own ions. Step 1, anions. The negative ions from the salt bridge, they migrate directly into the anodic compartment to neutralize that dangerous excess positive charge. Step 2, cations, the positive ones from the bridge, migrate into the cathodic compartment to completely neutralize the excess negative charge. By detailing this precise two-step migration, you're showing the grader, without a doubt, that you fully grasp the vital mechanism of electrical neutrality.
Okay, almost there. Step 3, preventing liquid mixing, which is all about maintaining efficiency. Now this step is brief, but it's incredibly crucial to your complete answer. You just need to simply state on your exam that the salt bridge strictly prevents the mechanical mixing of the two distinct electrolyte solutions. You know, why does this matter? Well, because if they just mix together mechanically, they would instantly undergo direct chemical reactions. You wouldn't get the valuable electrochemical work you actually want, like, actually powering a device. You just get a sudden, total drop in cell efficiency. So the salt bridge intentionally keeps the chemistry separated so the physics can actually do the work.
Finally, we arrive at the secret exam tip on ionic mobility. This is how you literally guarantee top marks. When discussing the inert electrolyte that you strategically chose way back at the beginning of your answer, you're going to want to write down this exact golden rule, loudly and proudly. The ions chosen for the salt bridge must have nearly equal ionic mobility.
And this brilliantly illustrates exactly why that rule exists in the first place. Take potassium chloride, for example. The potassium cation and the chloride anion, they migrate at the exact same rate. If one moved even slightly faster than the other, their own movement would create a brand new charge imbalance. But because they have equal ionic mobility, they don't generate their own liquid junction potential. The bridge gracefully avoids creating the very problem it's trying to prevent. It's just a stunningly elegant chemical solution, right? And clearly explaining this nuance is definitely going to secure you those maximum marks.
So let's leave with a little thought experiment. We've just broken down exactly how to secure an A on your exam, but step back for a second. This elegant mechanism of electrical neutrality, it isn't just for passing tests. It's literally the fundamental, microscopic foundation of the macroscopic technology we rely on every single day. If this delicate, precise balancing act is required just to keep a simple galvanic cell running, imagine the microscopic miracles happening inside your smartphone battery right now. Keep questioning, keep structuring your knowledge, and go ace that exam.